Okay, this is Jared Williamson. I'm starting a podcast called Advanced Survival, Preparedness and Survival. And in the last video, I talked about how basic filtration works. And I used a chemistry lab experiment with filter paper and funnels. But that principle is the same for what's called gravity filtration. What I'm going to talk, and in that video, I talked about how filters can filter out some things like viruses or bacteria or maybe heavy metals, but cannot filter out other things like sodium chloride from salt water or fluoride. And you have to have special filters for those. So what I'm going to talk about today is the adsorption filtration of fluoride and how there are certain special filters that can remove fluoride and other things from water. Usually for this, it's going to be fluoride, arsenic, and selenium. In the last discussion, I talked about how we had here at the basic chemistry setup, but the principle's the same behind all gravity filtration, where I run my polluted solution through a filter. In this case, it's filter paper. Out the bottom comes the filtrate, which is hopefully the purified water. Then the impurities are caught in the filter paper. And the reason why that happens is the filter paper, an extreme close-up picture, the filter paper has tiny little pores in it that lets the water through, but captures chemicals that are bigger than the pores. However, salt water can't be filtered to get the salt out. And that's because the salt water is made of sodium chloride dissolved in water, and it's separate sodium ions, separate from the chloride ions. And the water has a diameter of 282 picometers. 1 picometer is 10 to the minus 12 meters. Chloride and sodium's smaller than water. So if the filter paper has pores in it that will let water through, it'll certainly let things that are smaller than water through. And it turns out the pores are actually large enough to let chloride through too. So the problem with filter paper is if the pores are big enough to let water through, anything else about the same size will make it through too. Well, the reason why you can't filter out fluoride out of water is because water has a diameter of about 282 picometers, chloride is 362, sodium's 204, fluoride's 266. So fluoride can't be filtered out using regular filters either because it's smaller than the water molecule you're wanting to purify. And if the water molecule can make it through, the fluoride will make it through too. So what do? We use activated alumina beads, which are little beads of aluminum oxide, Al2O3, and it's really highly porous like activated charcoal or activated carbon is. So here I found a picture online of a fluoride filter. And this is, I put the name of what it is here because if I'm going to use the picture, I should at least say what the name of it is. And here I have these beads of activated alumina. And when I expand it, I see I have this bead and it's got a bunch of pores in it. Lots of holes going through this. It's probably got a surface area of about 200 square meter per gram of beads, which is really large. And when I expand it in even closer, I get the size of these pores. These pores are really small. Okay. The difference is in the filter paper, the pores let water through, but stopped the big molecules or big ions from making it through. Kind of like a screen door lets the air into your room, but stops the bugs on the other side. In this case, there's a close-up picture. These pores actually capture the fluoride. The fluoride goes inside, the selenium or the arsenic goes inside, and it gets trapped inside. Here's a picture. Now, I modified a picture that I found online to represent somewhat what activated alumina looks like or behaves like, and it's not that dramatically different than activated carbon or activated charcoal. So I have a picture of activated charcoal that I modified. But activated alumina has all these little pores, and the fluoride, selenium, or arsenic ions go inside of it. And fluoride, selenium, and the arsenic ions have a negative electrical charge. And deep inside these pores, they have a positive electrical charge. So what happens is when the selenium, the fluoride, or the arsenic goes inside, the negative electrical charge sees the positive electrical charge, and it goes straight to it, and it sticks on it, and it chemically bonds. And here I have pores that are large enough for both small and large ions, and here I have pores that are small enough for small ions. So these fluoride, negatively charged fluoride, selenium, and arsenic go inside the pores. They have negative charges. They're attracted to little areas inside here that have positive charges, and they stick to it. And here I have a nice quote. It says, think of activated alumina as a parking structure for fluoride, selenium, and arsenic. They go inside, they look around, they see that positive charge, and they park right there in that spot, and they stick to it. And let me move this. What happens is that they adsorb, adsorption to the surface, not absorb in. The fluoride goes inside the pores, but it doesn't go, it sticks to the inside surface of the pore, which is adsorption, where the molecules adhere to the surface of the material that's inside this little cave in here. It's because there's a slight positive charge inside, negative charge on the outside, opposite charges attract, they stick together, and they chemically bond, and that's called adsorption. In contrast, absorption is when the molecules soak into the material itself, like water soaking into a sponge. So, a little vocabulary word here today. Adsorption is they stick onto the surface, they're stuck to the surface, and they won't come off without a lot of work. Absorption is when it soaks inside. And let me back up a little bit, actually. So here, these beads have pores in it. The fluoride, selenium, or arsenic goes inside. They find positively charged regions inside, and they stick there, and they park on the inside surface like cars in a parking structure. Okay. And they get stuck there. Okay. And it's adsorption. They go inside the cave and they stick to the inside surface of the cave because of opposite charges. And that's different than filter paper, where the fluoride is smaller than the holes in the filter paper. So the fluoride will go right through the filter paper or other filters because the water goes through it. But here, the fluoride, selenium, or arsenic go inside, and because of opposite electrical charges, they adsorb to the surface and they're stuck there. And your Berkey water filters, let me move this again. They're not all that different than this filter that I found here. So these fluoride and arsenic filters have activated alumina in it. I'm not saying the inside of this is built like the inside of this, exactly the same, but they're close enough that you can learn from them. Okay, so that's the difference between gravity filtration with a filter and adsorption filtration using activated alumina and adsorption of the species onto the inside cave surface of the pores. Okay, and that's it for now. And I would appreciate it, a comment. I respond to all comments, and likes and subscriptions would be great too. All right, thank you very much.